Hello, everybody. Today's class is on optimization problems in MCV4U. There's two sections we're going to cover, but I'm probably going to do it over 2 or 3 videos. I don't want the daily videos to be too long. I might just do a couple of examples today, and I'll post them when I'm done. So, optimization with calculus applications involves trying to find the optimal or the best possible situation using modeling and functions. The best possible outcome, okay, is often under a set of restrictions. And it generally, with respect to functions and graphing and our work in calculus, it generally involves a minimum or a maximum situation. The endpoints have to be considered, and all the answers have to follow within our restrictions. So for some examples, optimization problems occur all over the place. We did a couple of optimization style problems before the break. I did one that very last day. I know not everybody was there, but I did show you one that we'll do again today. We talked about optimization problems when we found minimums and maximums in the last chapter, and optimization problems were indirectly seen when we did some velocity and acceleration questions. So with respect to some pretty regular standard optimization problems and optimization problems as they relate to economics, um, some topics and subjects of like in economics and business, some science optimization problems, we see some of the following common examples when we talk about optimization problems. Situations where we have to maximize profit or revenue of a company, right? We want to always operate under a maximum, getting maximum profit, and a maximum point is a hill, right? Right, is a okay, the top where the slope would flatten out and be zero. Minimizing costs, finding a minimum is when we want to actually produce something where we have minimal costs. Maybe maximizing the volume of a shape, about minimizing the surface area, right? Those two things might go hand in hand. We want to use minimum surface area, right? Because surface area is how we build an object. And often when we build something, we use materials, and we want to minimize the surface area because effectively we're minimizing the cost. And in certain situations, we want to find a maximum volume, okay, or a maximum area based on a minimum surface area or constraints that we'll talk a little bit about. Maximizing velocity, there's a good one, maximizing velocity and minimizing the distance traveled. So we're going to jump right in and do an example here, and this is one we've talked about and have done in the past. So here's the situation. Farmer with 2,400 feet of fencing wants to fence off a rectangular field that borders a straight river. Okay, no fencing is needed along the river, obviously. We want to have access to the water. What are the dimensions of a field that has the largest area? Okay, so we want to find the dimensions, okay, x and y okay, on our particular situation here, okay, where we have the dimensions. X we're going to represent the width, and y is going to represent the length of this shape. No, there's no y along the river, as I said. If we're a farmer, we want to create a pen. Let's say that we're going to put some animals in there. We want to be able to have them access the water, but we want to enclose it in. Okay, we have 2,400 feet of fencing. Okay, and we want to figure out the best possible area or the maximum area. Okay, so the first thing we're going to do is identify a couple of things here on my word problem. What I'm going to encourage you guys to do is read the word problem over, and then really quickly, and just get an idea of what is happening here and what you want to do, and then read it over a second time before you start it and identify some key things. Okay. First thing is the 2,400, a number in the question. That's good. We like numbers, right? So farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. So his fencing is going to go along this area. Okay, now that's perimeter. It's a modified perimeter formula. That's going to be 2x plus y, and that's going to equal 2,400. Okay, now I'm going to introduce our first term here when we talk about optimization problems. Okay, and this I'm going to call the constraint equation. Now, every optimization problem has a constraint equation, and this is very important. Okay, what a constraint equation means is that in this particular station, this is the constraint that the farmer's under. Okay, he or she has 2,400 feet of fencing. They don't have any more fencing. They want to use all the 2,400 feet of fencing. There's no practical reason why they'd only use 2,000, let's say, feet of fencing. That clearly won't give them the maximum area, right? So they might as well use the whole amount of fencing they have. They might have it in their barn, let's say, haven't used it in the past. It might be left over from an earlier project, and they just want to make a small little pen here. They don't want to have to go out and buy any more, right? They're under this constraint. Now, with constraint equations, one of the best things you should do is rearrange it, okay? So what would be the obvious way I can rearrange this in terms of one variable? How about y equals 2,400 minus 2x? Okay, great. So good. Let's just move along with the rest of the question. Wants to fence off a rectangular field that borders a straight river. Well, that's pretty clear on the diagram. We're lucky we have a diagram in this question. We don't always have diagrams, and if you can always draw a diagram and label a diagram, that's really helpful when you solve word problems. Okay, the second sentence, no fencing is required or is needed along the river. Okay, that's pretty straightforward. That's represented in the diagram. There's no real math there to do. Okay, and the next question is, what are the dimensions of the field that has the largest area? So I need largest area, and largest is a word for max here. So I'm going to underline largest area, and dimensions are what I'm asked to find here. Okay, so I certainly want to find a value of x and a value of y. That's going to be what I'm trying to do, my question here, that give this largest area. Well, area, I know according to this diagram, okay, it's a rectangle, so it's length times width. Okay, and this one's going to be called my optimal equation. Okay, my optimal equation is the equation I want to try and maximize, and that's mentioned in the question, right? Okay, I want to find the largest or the maximum area, and this is the optimal equation that I'm going to try and maximize. And I know area back from grade probably 7 or grade 8, maybe even earlier than that. The area of a rectangle is length times width. Okay, in this question, I'm going to use my variables here. So length times width, that's going to be x times y. That really doesn't matter, the order, right? I'm just going to write it as x, y. And now the next thing I'm going to do is write. So I've got my practical equation, area equals length times width, borrowed from my past knowledge in math, maybe the internet. I might have to look up, might have to Google an equation for volume or area at times if I forget. Okay, so I use my practical equation, then I use my variable equation, and then I'm going to write a function in terms of x. Now it's in terms of x this time because I just glance up here and look at my y, my constraint equation. My constraint equation is y in terms of x. So now I write my area as a function, my function in terms of x. So the actual equation for area is x, and y I'm going to replace with my constraint equation. So it's just a straight replacement. So now I expand it. And I've got an area function in terms of x. And that's going to be really important. Okay. Now, what should we do before we start doing the math here? I should talk about a constraint. Okay, an interval, a domain restriction, a restriction on our question. Let's write the restriction in terms of x. Now let's look at the diagram. This is how we come up with our x. Now let's look at the diagram and let's write our constraint in terms of x. I'm going to write x up here. Okay, what are the possible values I can have for x? Okay, so let's start with the lowest possible value I can have for x. Now, could x be 0? X is not going to be negative, right? Could x be 0? Well, yes and no. Okay, if x was 0, if I let x be 0, I wouldn't have a very big rectangle, certainly, but theoretically I could have most of my fence, okay, along the riverbank and a little wee bit, I'm kind of like this, right? Okay, Not a very practical pen. Okay, the animals won't be able to really graze and turn around here, but theoretically that's what my pen could look like. I could have a little wee x value on each side and then a really long y value. So here's how I represent this mathematically. Okay, so x has got to be greater than 0, but it can be really close to 0. Okay, so that's the inequality here. Now, what's my boundary? What's my highest boundary here? Okay, how high can x go? Well, x could go really high, actually. Okay, I could draw a pen that looked completely the opposite of the one I just drew. A pen that was really, really tall and not very long, and then back to the water again. That particular pen, oh, okay. Okay, that particular pen, this one right here, okay, okay, this particular pen, okay, is really long and narrow. Okay, okay, and it looks like I have two x's, so I could go as much as, and here's a little bit of math here, I could go as wide as half of 2400 because I need the other half remaining. Okay, so I could go 1200, 2400 divided by 2, 1200 feet up, okay, a little bit over, and then another 1200 feet down. It would be really narrow, but I could go, okay, okay, I could go as high as 1200. And there's my restrictions. Okay, that's the only value of x that can fit in there. Okay, and usually with a diagram in a rectangular situation here, it's the endpoints represent the most extreme sizes of the rectangle, right? Okay, so our answers have to be within that interval. If they're not, okay, then I can't make that drawing. Okay, so now I want to find the largest area. And the largest area is a maximum, right? And I want to find the maximum point here. Well, what happens on a maximum point of a function? This is a parabola function, parabolic, quadratic, right? So on a maximum, I want to find the slope of the tangent when it's 0, when it's a flat horizontal line, right? So that means this. Okay, so let's find the derivative of, okay, our area question. 24, okay, minus 4x squared. Oh, not x squared. I'm sorry. Okay. I think I've done that derivative right. Let me make sure, double check, right? So the derivative of the area function is 2400 minus 4x. Okay. The maximum, the flat horizontal slope will be when this is 0, right? Because that's the slope of the tangent, right? It represents that function. So okay, I have to solve that equation. Okay, so when I solve that equation, okay, what do I get? Okay, so the width of the pen should be 600 feet. Okay. Do a domain check, right? That's a good answer. It falls in my interval here. Okay, 600 lies right in the middle. Okay, so if my pen is 600 feet wide, and what would the y value be? Can I use my, what was that, 2x squared? No, sorry, minus 2x. I think I would get a y to be 24. So the dimensions for maximum area 600 meters by 1200 meters. Okay, good. Okay. So that's it. That's how you do an optimization problem. Now, one small thing is we might be asked, we weren't in this question, we were asked the dimensions and I answered the dimensions. We might be asked, though, what is the actual largest area? And that's an easy thing to do. I look for one of my equations for my area, and I can use either one. The easiest one to use is the first one. It's just x times y, right? So my area, if asked, my area is, I don't know what's that calculation. I don't have my calculator here. 72, 1, 2, 3, 4, going to be meters squared. Okay, good. Make any sense? Okay. That's the process, and that's sort of the style for optimization style questions here. All right, let's move on. Okay, do another one. This is a good one. This might be it. I might have to do this in a couple of videos. All right. Okay. A rectangular sheet of metal, 60 by 30, okay, shown in the diagram, is used to make a rectangular box with an open top. Determine the dimensions that will give the box with the largest volume, so maximum volume in this case. All right, here's my diagram. Okay, it looks like, okay, I show it down here. Now, what's happening here? I've got a flat piece of metal, 60 by 30, and I'm going to cut, what's going to happen here is I'm going to cut this little corner out. I'm going to cut this little corner out. I'm going to cut this little corner out. And I'm going to cut and remove this little corner out here. Okay, so now I'm going to have a diagram that looks like this. I'll do my best to try and draw this. Okay, and I'm going to fold here and here. Okay, and just bend pieces up. It's almost like I'm creating a net, right, of an object here. That's my flat two-dimensional look of this piece. And when I fold along the bends, I've got, sorry, when I fold along the dotted line here, I've got my open box, right? Okay, no lid on it. Okay, I've got that open. And my dimensions now, okay, are x, right? Because the x is right in this area here. So the height of my box is x, and I've got some funny dimensions for my new width. These are the dimensions of my box right in here, okay, the length and the width here. Now, it looks like that should be, okay, that should be here. 60 is the whole thing, and I take an x out, and I take another x out. So I take 2x out. And this dimension here is 30 minus 2x. Okay, now that's worth talking a little bit about, okay? So my original box was 30 centimeters, and I've removed one x from this corner and another x from this corner. So effectively, I've removed 2x, and what remains is the dotted width here. This line right here, okay, has a dimension of 30 minus 2x. So the dimensions of my box, okay, are 60 minus 2x, 30 minus 2x, and then x. Okay. Now volume is, okay, volume is length times width times height. Okay. And in this case, okay, in this case, I can write my volume in terms of x. Okay. So I kind of had a constraint equation. Okay, it's under the constraints of this material, 60 minus 2x and 30 minus 2x and x. But my optimal equation is going to be 60 minus 2x times 30 minus 2x times x. Okay, which I'm going to expand all out and, okay, factor and see if I can find my amount. Before I do that, let's talk about the the domain restriction, right? How much material can I use, or how big should this be? Now it has to do with x, so we have to do it in terms of x. Okay. Now how big a cut is that? Basically, that's what this means. How big a cut is this? Okay. How much can I cut out of this side? Well, that cut, that removal of that square, I could go down and I have to take it out of both end pieces, right? Both corners. So how much could I cut here? I could cut a little wee bit. Okay. So a little bit greater than 0. The cut might just be a little bit. And I can go as high as 15. And again, that's half of 30, right? And that's because I've got to make 2 cuts, similar to the question we just did. So the cut that I can make, okay, it could be a little bit greater than 0. That would be hardly a cut at all. Okay, and a little wee bend and a little wee fold. So my new object, this box with the open lid, would actually be really flat and not very tall. Or I could go all the way to 15, right? Almost 15, right? All the way up to 15. That would mean not a very, it'd be a pretty narrow box. Be tall, really tall box, but it'd be a pretty narrow box. And that's the constraint I'm looking at. Okay, let's expand this. Okay, let's expand this. I'm going to do all the work here to expand it. I've done this already, so I won't talk through this. Okay, I'm just doing FOIL on. Okay. Okay, so it's going to be a cubic. Okay. Okay, and that's my volume function in terms of x. Okay, and it's a cubic equation, right? Because there's 3 dimensions. Okay, maximum volume. Maximum volume. That's what we're trying to find, right? So I need the derivative. Okay, so if you can develop the optimal equation and take the derivative of it, you're pretty much there. Okay, what is the derivative of this question? 1,800 minus 2 times 180 is 360. So it's a negative 360x. Okay, and then a plus 12x squared. Okay, we learned this the other day. Cubic, the derivative of cubic is always a quadratic. Okay, now I got to set that equal to 0. Okay. Okay, can I set that equal to 0? And solve for x. Good, sure I can. Well, let's take a greatest common factor out. What can we take a greatest common factor out of? I think I can take 12 out of everything. If I take 12 out of everything, I'm going to be left with 150, okay, minus 30x plus x squared equals 0. And the 12 cancel. I can divide both sides by 12. The 12 basically cancel. That greatest common factor cancels. So now I'm just going to rewrite that a little bit. Now have to factor it. Okay, can I factor that, or is that easily factored? Remember, my goal is to solve for x. X is the cut I'm going to make out of that. I can try and play around with it with FOIL a little bit. What are some factors of 150? Give me 30. 15 and 10 aren't going to give me 30. 50 and 3 is not going to give me 30. Anything else of 150? There's probably others. I might graph it in Desmos and get my roots and my factors. If I can always cheat and do that, I just look at the zeros. Or I can use the quadratic formula. Okay, remember the quadratic formula? X equals minus b plus or minus the square root of b squared minus 4ac all over 2a, right? I think so. Good. Okay, quadratic formula gives me the roots in a, not a fast way, okay, but certainly, okay, it gives me the roots if I know how to use the quadratic formula. I'm going to leave the work for you guys to do. The quadratic formula, though, works out to be, and there's 2 roots. I have in my notes here beside me. Okay. Now what? What did we do in the last question? have my answers for x, my possible answers, and I scroll up to my interval restriction. What do my answers have to lie in between 0 and 15? So this root, okay, is inadmissible. Okay, and this one's my answer. It lies in my interval between 0 and 15. Okay, and the 23.6 doesn't. Remember, quadratic formula on a parabola gives me at most two answers. There's two roots here. Okay, and the cut has to be, okay, the cut has to be that amount. So what are my dimensions? Dimensions are, okay, what's my length? My length, my width, and my height. Well, my height is my value of x. And I think it's, what's in centimeters? Was it in centimeters? Yeah, it was in centimeters. Okay. My length is 60 minus 2x, and x is 6.34. Okay, so that works out to be, I have in my notes, 47. Okay, and my width is 30 minus 2x. X is 6.34. And again, I have in my notes, I think 17.36, I believe. All right, good to go. That's it. That's my dimensions, and just confirm, is that what I was asked for? What dimensions, determine the dimensions that give the box with the largest volume. And I know it's the largest volume because I did the derivative and checked and found that maximum point. Okay, remember that. Okay, that slope, that's the volume function. That's the point I found, and it was at 6.34. All right, good. That's about 30 minutes. I only covered two. I'm going to have to do a variety of different optimization problems here in order to make sure we know how to do some of these. So continue with your work, and we'll talk to you tomorrow, and I'll record another video soon. Thanks. Bye-bye.